Welcome to the deep dive. Today we're tackling something, well, pretty fundamental and definitely complex. We're diving into Latham Hayes' postmodern unified theory, or UPT. Specifically, we want to understand the mathematical heart of its core force, the tensor force.
Yeah, this source material is dense. It's packed with equations, boundary conditions, the works. But our mission today is to kind of decode it. We want you to get the logic behind how this force, this tensor dollar, actually comes about, how it's defined just from the system's own internal state.
Okay, and to even start that conversation, we absolutely need to lock on to the key variable here, mass intensity, symbol or dollars.
Exactly. Step one. And you really have to shift your thinking here. Forget density as just mass divided by volume, like an average, or dollars is the point quantity of mass intensity. Think of it as the vacuum's intensity at one single specific point in space. Hyperlocal. SI units are kilograms per cubic meter, sure, but conceptually it's a property of space itself right there.
So wait, if I$ is a vacuum intensity, are we saying mass isn't particles fundamentally? It's more like a local bump or feature in this intensity field?
That's the big conceptual shift, yeah. UPT suggests I$ is the underlying state, this density, and physical mass, I$ is what emerges from it. And the theory clarifies this mass convention. 1 molar, they set kappa to 1 kilogram in SI units just for convenience. So the quantity Q there is basically the same as mass dollars, and I$ is just the measure of that quantity Q per unit volume at that point.
Okay, let's unpack this then. Starting with the rules, because this isn't just equations thrown together, is it? There's this whole framework, these foundational rules, the FBK, foundational knowledge-based principles that kind of constrain everything.
Exactly. They're the guardrails, essential. If something violates these FDK principles, it's out. And the first one, FBK endogenous, might be the most important for making the theory unique.
Endogenous, meaning it all comes from within, internally generated.
Precisely. The bulk, the inside of the system. It can only use the intensity all at that point in time, or whatever, and how it's changing in space. It's gradient, nabla, that's it. No bringing in outside gravity fields or predefined geometries or other forces. Force itself has to rise just from nabla and nabla-I.
Which makes sense then for the second principle, bulk boundary separation. You got to keep the pure inside stuff separate from the messy outside interactions.
And it's a strict separation. Things happening at the boundary, like this fountain potential phase or loads to Keeler, they stay at the boundary. They sort of manage the interaction, yes, but they can't just reach in and change the fundamental physics derived from lob inside the bulk.
Then rule 3, super important for any physics, closed work energy.
Right. The tensor force you derive, it has to produce work at the boundary that lines up perfectly with these FBK rules. And energy has to be bounded. You can't have energy dropping infinitely low. No perpetual motion machines here.
Makes sense. And finally, rule 4, locally, things have to be isotropic. Direction shouldn't matter intrinsically.
Yes, at least in this first order theory. Locally, deep inside the bulk, the material response only cares about the magnitude of the gradient squared nabla-I 22. Not its direction. The system itself doesn't inherently know up from down unless a boundary condition somewhere tells it.
Wow. Okay, so those are pretty strict rules.
Yeah.
And they immediately force the energy density into a very specific shape, right? Not much wiggle room.
Exactly right. That tight structure dictates the form of the internal bulk energy density, epsilon bulk. It has to be. Epsilon bulk, I, tel I plus BI.
Okay, let's break that down. What are AI and BI doing?
So think of a Kali as the background state function. It's like the potential energy density you have, just because the intensity is $1 at that point, even if it's totally uniform everywhere, the inherent potential.
And the second bit, times the gradient squared. That's the energy cost of variation.
Yeah.
Of change across space.
You got it. That term is the energy stored, because U-Dillers is changing from point to point. U-Dillers is the coefficient scaling that gradient energy contribution. And crucially, U-Diller must be 0 or positive. That's vital for stability. You don't want energy to decrease when gradients increase wildly. And unit-wise, it all checks out. U-Dilla-Dello and epsilon bulk all end up with units of joules per cubic meter. Energy density.
All right, so we have the energy pinned down by the rules. Now we get to the force itself. The tensor force, this is the stress tensor, right?
Yes, it's how those energy variations actually exert forces, the push and pull within the material or medium.
And the main equation looks like BAI plus BII, Y, that specific form.
Well, you can see it splits into two main conceptual pieces. The first part, the $2 EI Mele I term, that's the directional part, the anisotropic part. This force component acts along the direction of the gradient, where the intensity is changing most rapidly. Think of it as tension or pressure specifically caused by the inhomogeneity.
Okay, so that's driven by the change. Then there's the second chunk, which is basically the total energy density, epsilon bulk, times the identity tensor math bulk, but negative. Why negative? And why proportional to the total energy? Is this like a pressure pushing outwards equally in all directions?
Wow, that's a great way to think about it. Yes, that's the isotropic part. It acts like a generalized pressure. It ensures the energy stored in the bulk resists compression or expansion uniformly. It's the system's inherent resistance, pushing back against everything equally.
Now, here's where things get even more interesting, mathematically speaking. That tensor force isn't always symmetric, is it? There's this extra conditional bit, the asymmetric component, TDC.
Right. Tut. This only shows up if a specific condition called conditional covariance or amchin-kodil kin is switched on, essentially. If it is active, then you add this term, skew noblesse. Here, $2 is some vector field, and the dollar is another coefficient function.
Okay, hold on. Conditional covariance. And skew noblesse. Why would we need this asymmetry? If the energy itself is isotropic, where does a twist come from?
It comes into play for potentially more complex dynamics, maybe involving local rotations or twists within the bulk that aren't captured otherwise. But the really neat part is the skew noblesse term. That skew operator is key because it ensures something called gauge invariance.
Gauge invariance. Okay, quick refresher for maybe some listeners. Why is that important?
Well, imagine you have this vector field, $6, and you decide to measure it slightly differently, maybe shift your reference points. That's a change in gauge. If your physics change just because you changed your description, that would be bad. It would mean you're calculating forces that aren't real. The skew operator mathematically ensures that only the physically real rotational part, the part that doesn't depend on your arbitrary gauge choice, contributes to the force. If that covariance condition isn't active, $2 is just zero, TC vanishes, and the whole tensor dollar stays symmetric. Simpler situation.
The level of mathematical rigor here is impressive. It's not just, here's a formula. It's, this formula is necessary. You mentioned the theorem of first-order endogenous FBK uniqueness.
Yes, and that's a cornerstone. That theorem basically proves that given those 5 FBK assumptions we started with, local, first-order, isotropic, etc., these exact forms for the energy, epsilon bulk, and the bulk tensor Talbot are the only possible ones. You can't follow the rules and logically end up anywhere else. That's what gives the theory its mathematical backbone, its self-consistency.
Okay, so that covers the pristine interior, the bulk. But physics happens at the edges too. How does this internal force connect to the outside world? That brings us to boundary conditions and this thing called the traction vector.
Right, the traction dollars. That's the force per unit area exerted by the system on its boundary. It's how it pushes or pulls on its surroundings. And its definition starts with the bulk force acting on the surface. That's the T-gut non-term, where not only is the surface normal vector, but then adds some crucial boundary-only terms.
And these extra terms are vital, aren't they? They let the system handle things we normally think of as external effects, but without breaking the internal rules.
Precisely. 2 key ones stand out in the source. First, there's a term for jump discontinuities, something like delta I, and dollar. This handles situations where the intensity dollar suddenly jumps as you cross the boundary, like at an interface, think surface tension effects, that kind of thing. Delta I is the jump size.
And the second one involves that found-in potential again, partial pi, the normal derivative.
Yes, the found-in potential, Phyllis. It's really the boundary regulator. It's the sophisticated piece that lets the purely I-dollar-based internal physics interact with specific external conditions, like applying a load, or thermal effects, or joining different materials without violating those core FBK endogenous rules. It acts like a translation layer, mediating between the internal world of dollar and the external boundary conditions.
This leads to a really fundamental question about dynamics, about motion. The source says UPT gets consistent dynamics without needing a separate inertial force, like R. How does that work? That's a huge departure.
It is perhaps the biggest departure from classical thinking. Usually you sum up forces, then you have this separate concept of inertia, mass times acceleration, on the other side of the equation. Here, inertia isn't tacked on, it's meant to be inherent in the evolution of I-dollar itself.
Are you saying Newton's second law is kind of emergent from how the intensity field dollar changes over time?
That's the idea. The dynamics, the motion, the changes over time. They are governed entirely by the partial differential equation that describes how $y evolves. The tensor force dollar primarily comes into play when you calculate work at the boundary. The actual physics of motion is all encoded in the PDE for $5.
And the source mentions two main flavors for that time evolution.
Yeah. Commonly a wave mode, which involves the second time derivative, partial 2t. That one naturally keeps inertial-like behavior. Or a diffusion mode, using the first time derivative, partial $I$. This often neglects inertia, suitable for slower, quasi-static problems where things change gradually.
Okay, let's talk resilience. How robust is this mathematical structure? You mentioned reparametrization and variance. Sounds important.
It's crucial for consistency. It basically means that the physics predicted by the theory shouldn't depend on the specific way you choose to measure or scale the intensity of dollars.
So if I decide to use, say, the square root of $r as my main variable instead of other itself, the final physical outcome, the forces, the energy should be exactly the same.
Precisely. If you re-parameterize $I$ into some new variable I, using a function like y of iy, where $5 is monotonic, always increasing or always decreasing, the total energy epsilon bulk must not change. And for that to happen, the coefficients, again, have to transform in a very specific, predictable way to compensate for the change in the variable.
So I aren't fixed constants then. Their functional forms depend on the choice of dollars as the variable.
Exactly. They adapt. For instance, that directional coefficient bi has to transform according to half I2, where $5 is the derivative of the transformation function. This ensures the energy calculation gives the same result. It's a sign of a robust theory. The physics is deeper than the specific mathematical description you happen to use for $1.
All right, let's shift gears slightly to the practical side. How would you actually use this theory? Say, with standard SI units, calibration seems like the big hurdle.
Oh, absolutely. Those core functions, DAIR, they are not universal constants handed down from above. They need to be determined experimentally. You need real-world data specific to the material or system you're modeling to figure out the exact shape of these functions.
And the sources highlight a really important catch in doing that fitting, right?
Hey.
Something about needing variation in multiple directions.
Yes, that's critical. To properly disentangle the effect of the background potential Syria from the gradient-dependent part involving Belozi, your experimental data must include situations where the intensity of dollar is varying in at least two independent spatial directions.
Why two? What happens if you only have, say, a gradient along the x-axis?
If you only have variation in one direction, mathematically, the contribution from an I and the contribution from bad I die times the gradient squared get mixed together in a way you can't separate. You could fit the combined effect, but you wouldn't know the individual functions uniquely. The parameters are underdetermined. So you need complex experiments measuring gradients in multiple dimensions, and naturally, any functions you fit have to pass that basic check. The total energy epsilon bulk must always be non-negative.
And just briefly, to reassure us that this isn't just hand-wavy math, there are actual proofs behind this: existence, uniqueness.
Yes, the mathematical foundation seems solid. The sources mention proofs, likely using techniques like the Lax-Milgram theorem for the weak formulation of the problem. They show that if you provide reasonable boundary conditions and enforce a coercivity condition, which essentially means must stay strictly positive, not just non-negative, then the static problem is guaranteed to have one and only one solution. It means the theory is mathematically well posed. It should give you a single, sensible answer. These are important safeguards.
Okay, so let's try to pull this all together. We've taken a deep dive into the mechanics of this tensor force in UPT. We've seen how it aims to define force completely from within, just using this local mass intensity dollar and its changes in space, its gradients. And it does this while sticking to strict foundational rules, achieving uniqueness, consistency, even handling dynamics without a separate primidia.
That's the essence of it. The tensor force isn't just postulated. It emerges as a mathematical necessity from those 5 FDK principles: local action, separation of bulk and boundary, and so on. It's an ambitious attempt to describe interactions, tension, pressure, even dynamic effects, purely as manifestations of how this underlying intensity field dollar behaves. The real challenge now, as we discussed, is getting the high-quality, multi-dimensional experimental data needed to actually pin down those state functions in the body for real-world applications.
Which leaves us with a pretty profound final thought. If this framework, defining force entirely through the internal dynamics of a single quantity, like $80, proves to be more than just a theoretical construct, what could that imply? Could phenomena we currently explain with separate fundamental forces, gravity, electromagnetism, eventually be understood as just different aspects of the complex evolution of this one mass intensity field? It certainly gives you something deep to ponder about the nature of force itself.